Okay, hi everybody. It's been a little bit since we've posted a video, but after a busy summer, we are back, hopefully helping people learn a little bit of practical optics stuff from our lab here at the University of Maryland, Baltimore County. So today, what I wanted to talk about was optical alignment and sort of my philosophy on optical alignment, some tips and tricks. I think this is one of the most crucial things that you can learn in an optics lab, and yet it's very often taught really informally, and I think people don't understand the underlying ideas of why we do the things we do when we align things. So the first thing I want to talk about is the two types of alignment that I think are relevant. And those really break down into absolute alignment and relative alignment, right? And so absolute alignment would be, I have a beam and I need it to be in an exact position in space, regardless of what relative optics are around it. That's what I would call absolute alignment. Relative alignment would be something more akin to, I have an optical component, such as a lens, and I need to make sure that my beam is aligned to the optical axis of that component. That's what I would call a relative alignment. And for me, I approach those two different kinds of alignments with different strategies. So before we get to the hands-on stuff, I'm going to show you. You can see I have a little setup here on this desk in my office. I first want to discuss what a line is and how we can define a line, right? Because the propagation path of our laser in any given section can really just be thought of as a line segment. And so let's go over to our whiteboard here. Hopefully you can see what I see. And there's two ways that we can define a line, right? Right here. The first of which is we can define 2 points, right? If we have 2 points, then there is one and only one straight line that perfectly connects them, yeah? The other way that we can define a line is to define 1 point and then define an angle from some axis at which the line emanates from that point, right? This is another way to define a line. Now, the reason I bring this up is because the way that we do optical alignments is we make a measurement that looks like this. However, our control parameters for tuning that alignment really looks more like this, okay? And this is because the way we do this, hopefully you guys can see what I'm seeing, is we take mirrors, right? And irises. So you can see this in this setup right here. I have my laser coming out of this fiber. This is just a lens to collimate it. Then I have 2 mirrors and 2 irises. And these 2 irises are screwed directly into the line of holes on the table. So I know that if I have my beam going through these 2 irises, then my beam is going at exactly the same height along this line of holes, right? That's this kind of definition of a line. That's how we're doing the measurement. However, since we're using a mirror, really we can only control the angle of that mirror with these sort of actuators on the back of the mirror, right? And so really what we're doing with the control parameter is to do this. We're changing that angle. And so what we need to think about is how this works out in practice, right? And so what most people will tell you to do this alignment is that you take your first mirror, this one here, and you use it to center the beam on the first iris, this one here, if the beam is propagating like this. Then you take your second mirror, use that to center your beam on the second iris. And you do that over and over again, iteratively, until your beam passes perfectly through both irises. And this is a perfectly sound way to do things, but I want to think a little bit deeper about why that works and how we might make these alignments more effective. And so let's take a look at this diagram. Here I've just drawn a beam coming in. It hits this first mirror that I'm calling M1, then it hits a second mirror that I'm calling M2, and then it travels along some path through 2 irises, I1 and I2. I've also defined a couple distances. Delta X here is the distance from the perfectly aligned axis that the beam hits the mirror M2. And then delta X1 and delta X2 are the positions that it hits each iris relative to that perfectly aligned axis. Now D1 and D2 are the distances from those irises to, oops, this one is actually not drawn correctly. It's the distances from these irises to the mirror M2. Okay, so if you run through the math of this, it's actually pretty simple to figure out how far off your beam should be given initial conditions, right? So delta x1 is going to be our initial starting position, delta x, plus d1, that's this first distance, times tangent of the angle that it comes off of the mirror M2. This is pretty easy to convince yourself of. I encourage you to think through the geometry of why this works. Delta x2 now is essentially the same thing, but now we have our initial delta x plus d2, this larger distance, tan theta, okay? Now what we really want is for our changes to these mirrors to be completely independent from each other, right? We ideally want only one of these parameters to change one of the things we are interested in. In this case, what we're doing is, again, our measurement is like this measurement of a line where we have 2 points, but we can control these two things, right? So our mirror M1 will deflect our beam such that it hits M2 in a different position. And so really what M1 is doing is setting the position of the beam on M2. Thus, we want M1 to really only tackle this delta x parameter, okay? Then with M2, we're changing the angle at which the beam comes off. And so ideally, we would have it such that M2 only affects this theta parameter, right? If we could do that, then we could independently decouple these things, and that makes our alignment much easier. Okay, so how might we do that? So we can see if we take a look at the math here, that ideally, what we would do then is we would set this D1 term to 0. If we move this iris infinitely close to our mirror M2, that whole second term cancels out, and we can just use x1 to exactly set the position on our first iris. Now, in practice, this is not possible, but still what will make your life easier is to minimize this distance. And so typically you want to put it as close as possible. You can see here, I've got about 3 inches between my mirror M2 and my iris I1. This is mostly so that you can actually see the iris on the camera as I'm going through the demonstration. But in general, I would have this much closer, ideally as close as possible. Okay, so there's not really anything we can do to decouple these two parameters, but M2 actually doesn't change delta x. So luckily, when we change M2, we actually really are only changing this theta parameter. The offset will still include our initial delta x, but changing M2 doesn't change that. And so in this way, we can actually pretty heavily decouple these things. The other thing we want to think about is how can we make this alignment as accurate as possible, right? We want our alignment to be sound over a meaningful distance. And so what we really want to do then is increase the sensitivity of our effective measurement of this angle theta. And so we do that by making this distance d2 as large as possible, right? The larger we make that distance, the bigger this deflection delta x2 becomes, and so when we are aligned, we know that alignment is more precise. Okay, so hopefully that all makes sense. I think some of the confusion and some of the nuance of this is that we're making a measurement, again, based on defining a line by 2 points, but we're really controlling the position of that line by controlling a position and an angle. And so there's just a couple things that you need to think about critically when you're setting up your alignment apparatus to really make that work out. Okay, so with that, let's go back to the table or to the desk. I'm going to adjust my camera here so that hopefully you can get a better view of what's going on. And so let me just quickly run through what we have set up here again. So here we have a fiber laser output. I'm collimating it with a lens here, and I simply have 2 mirrors for steering, 2 irises for checking the alignment, and then I have an SM1 housed optic here for the next part when we talk about relative alignment. Okay, so let's turn on our laser. This will take a second to warm up. But the laser is a 638 nanometer diode laser, so hopefully it's very clear on the camera. You can see it hitting this mirror here. We're hitting this second mirror here, slightly off an ideal position. And as you can see, hopefully, we are not well aligned to either of our irises, but we can fix that. So typically when I do these things, I like to start with the second mirror, this angular mirror. And so I'm going to open my first iris. I'm going to look at where I am on my second mirror. As you can see, we're clipping on the mirror surface, so that's not going to work. So first things first, I'm just going to move this first mirror until we have our beam completely on the second mirror. Great. And now I'm going to check where our alignment's at. So again, I'm going to use my second mirror to align to my second iris. Now, what you may notice, hopefully you can tell this in the video, is that my aperture here is much smaller than my beam spot. This is not good because this makes it much harder for your eye to discern small differences in the centering. And so what I like to do is open my iris until there's just a small halo around it. And you can see, if I have my iris set here, visually this looks pretty well centered. As I open the iris more and more, you can start to see that there's definitely an imbalance, right? There's a little more brightness on the top than on the bottom. So I'm going to adjust appropriately. Great. So now that I have my beam going through one iris, I now need to check my second iris. And you can see that that's quite far off. So I'm going to use my first mirror, M1 now, to fix that. And what I'm doing, remember, is I'm really fixing the position on the mirror M2. Okay, that looks nicely centered, but obviously when we change the angle of the beam coming onto M2, that's going to change the angle of the beam coming off of M2. And so now we need to iterate. So I'm just going to go back and forth and do this a few times until both of these irises are aligned. Now, one thing to note is that the shorter the distance between these two mirrors, the more iterations this is going to take. For the same reason as we talked about before, is that these angular deflections will make smaller deflections in the position of the beam. And so if you have the space to put a lot of room between these two mirrors, it will probably make your alignment slightly less of a headache. So it does seem as though I have set up my optics in such a way that maybe my beam is going to be slightly clipping on the mirror's edge when it's nicely aligned, but that's okay for demonstration purposes. I'm not too worried about it. But we can see, so there's a little bit of clipping here. Come in a little bit further. Otherwise, you can tell it looks very nicely centered on this iris. If I open that iris, it also looks very nicely centered on this iris. So that's really all you need to do for this type of optical alignment. Again, this being that absolute alignment where I need my beam to be in this exact line in space over some distance. Okay, great. So we've used what we learned on the board over there. We've applied it here. Fantastic. What if, however, we don't know exactly where we need our beam to be in space? How do we then do this? Or even better, what if our optical component doesn't perfectly align with the whole grid, right? So what we've done here is we've set our beam in a known position, and now if we had a lens, we could screw it in a position where we know it's exactly centered with the whole grid, and we could go from there. However, as you can see here, I have this 90-degree mirror mount, and the way that these are machined, the optical axis of the mount is not aligned to the hole that it's screwed into. You can see this because we know we have aligned our beam to this line of holes, and yet we hit it off center on this mount. So what do we do in this case? Well, now we can further exploit what we talked about over there by using these little alignment tools. I make these in the lab all the time. This is really just a combination of two simple components. If I can pull this apart and show you, it's a little stuck together, so maybe I won't pull it apart. But this is essentially just a small lens tube with an old scratched mirror placed in it. Now this mirror is facing back this way towards us, and on the other end, I've put an iris, okay? So what I'm going to do, block the laser beam, I'm going to open this little cap I have on here, and I'm going to put my tool into that threading. Now, if your component is not SM1 threaded, you'll need to make one of these that has the correct threading. We typically buy everything from Thor Labs, and standard Thor Labs components typically have SM1 threading. Okay, so now what I'm also going to do is I'm going to remove this iris. Now, we're going to slightly change the way that we're doing things now, where we're going to use this iris that's on the mount as our first iris, right? This sets the position as close as possible to the center of the optical axis in this mount, right? Now we don't care about absolute positioning, so this iris doesn't really help us. But we know that we need to be along the center of this SM1 hole, and so we place an iris right there. The mirror then is going to back reflect our laser beam. Actually, I'll take this one out as well. And what we're going to do is we're going to make sure that the back reflected beam overlaps the beam that's going in. That will act as our second iris, and you'll see what I mean when I turn the laser beam back on. Okay, so I'm going to turn the beam back on. I'm going to put a card in the way just to make sure the beam's not flying out at an angle. Okay, great. So let's go through what I mean. So I'm going to take my first mirror and I'm going to align to this iris. And it appears as though, because of the shift in things, I will likely have to move my second mirror somewhat. And so I'm going to do that. Okay, hopefully that's enough. Okay, so let's try that again. So I get my beam centered on the iris here. That means that relatively close to the mount itself, I know that I'm centered. But we also need to make sure that we're going in normal to the machined face of this surface. And really, we're trusting a lot here that all of these machined surfaces are actually what they're stated to be, right? This is a 90-degree angle, that this is perfectly flat, but machine tolerances are quite good, so I think that's safe. Okay, so now I'm going to open up that iris, and you can see, if I look at this first mirror, hopefully you can see this on the camera, that there's a second replica of the beam. Let me move it up so it's a little clearer. That's our back reflection, right? If I block the beam here, that goes away. And if I remove that card, that comes back. So now all we need to do is center these two beams on top of each other, because what that is saying is that the beam I send in is coming back exactly in the direction that it came from. And what that must mean is that my mirror, if it is exactly normal to this surface, and my beam are exactly normal to each other. Okay? And so again, this is an iterative process, so we can see we've slightly lost the alignment on this iris. And so I'm just going to use my mirror M1 again to fix that. And then we'll open it up and take another look here and center the beam on top of itself. And we'll just go through that a few more times until everything looks relatively good. That looks nice. This also looks nice. Now when you do this, ideally you would propagate the beam as far back as possible, right? Again, that will increase your resolution like we talked about before, and the sensitivity of your alignment. Okay, so I'm doing a couple of last tweaks. And patience is a virtue here. Slow and steady wins the race. You don't win any awards for aligning quickly. So just be patient and trust the process. You should converge on a nicely aligned beam. Okay. So I think that looks relatively good. Great. So now what we know is that we have aligned ourselves to the optical axis of the mirror in this 90-degree mount. But I want to show you one last thing, and that is, the point of this 90-degree mount is that we can have a beam that is exactly turned by 90 degrees, right? But there's also a mirror in this mount. And so I'm going to take out this other cap. And so how do we ensure now that this is turning the beam at the correct angle? Well, I have a similar kind of alignment tool for that, where I've again just put a mirror in a lens tube, but now there's no iris. And so I'm going to put that, I'm going to turn my laser beam off for 1 second. I'm now going to put that in the second, the output aperture of this mount. And so if we trust the alignment that we just did, what we should be able to believe is that our beam is exactly centered on the optical axis of this mount, and that it's propagating directly normal to this surface. So if that is the case, it should hit this mirror directly in the center. And if this mirror is turned at 90 degrees, then this should go exactly out normal to this 90 degree surface. So what we're going to do now is we put our second mirror in here such that it back reflects the beam again. And now we just need to turn this mirror to back reflect the beam on top of itself. So I'm going to turn the laser beam back on, and you'll see that we're way off, right? My beam isn't even hitting M2, okay? So I'm going to fix that. And again, what we're trusting here is that, oh no, my cap came off. That is all right. I'm going to grab a 564 driver, and we'll just do it that way. So again, what we're trusting is that the machining process that makes these components is accurate, right? We're trusting that when Thorlabs tells me that this mount is an exactly 90 degree housing, that it is exactly 90 degrees. And you know, these are the sort of things that as scientists we should always check. But in general, machine tolerance on a CNC is very, very good. These things are probably accurate to microns. And so I usually trust the machining. For very, very precise optical components like microscope objectives, you will still want to have some additional fine-tuning procedure. But definitely for coarse alignment, this will get you 90% of the way there, if not more. Okay, so I think that kind of covers everything I wanted to talk about. I'll actually take this mirror off so you can now see. Hopefully it's not going to hit anything, but we can now see, yeah, it does kind of hit this here, but our beam is coming out very nicely from the center of this output port and is traveling normal to it. Okay, so yes, hopefully this is helpful. If you are in my lab and you have any questions on alignment or tips or tricks that you think you might need, please feel free to ask me. If you are not in my lab, as always, you're welcome to ask questions in the comments section or to reach out to us through our lab website, dieterichlab.com. Hopefully this is helpful, and we will see you guys in the next video.